Hello everyone, this is Jin from Dolby, and I'm pleased to present our work, Stimpack, an adaptive rendering optimization system for scalable cloud gaming. Let's get started with the background and motivation. Cloud gaming runs a game instance on a remote server and streams the rendered frames. So the user experience in cloud gaming is determined by FPS, the frame per second, how smooth it is, and then the visual quality and how the frame is visually realistic and vivid. And last one is the low latency, is about the responsiveness. So this makes the cloud gaming services are hosted at the edge of the network, but it is with the fundamental dilemma because of the location trade-off. So when you think of, as we all know, the centralized cloud has a high scalability, but it's with a high latency network. So let's say from the user distance perspective, so it causes the poor service accessibility. So when you think of the edge servers, why they can provide the computing resources at the lower latency network connection, but they are usually provisioned with the limited resources and creating the scalability bottleneck. So how this is addressed in the cloud gaming services, so they limit the user's playtime. So whenever the nearby the game servers are fully occupied, the users are queued to maintain the serving users' quality of service. So this causes the issue of the low service availability. So in this work, Stimpack, so we address this issue by increasing the per GPU scalability. So technically means the number of the users can be served with each GPU. But while doing that, so it is also important to maintain the quality of service, and that's our goal. Let's talk about the opportunity. So the core insight for Stimpack is there can be inefficient rendering effort. So in cloud gaming, the user perceived frame quality is determined by the two things. So first one is the rendering quality on the server side. So and the second one is the compression quality, which is induced by the user's network condition. So the sample game scene on the right side here, so compared to the low rendering quality, the high rendering quality takes 3.6 more rendering time per each frame. So when the user is in a good network condition, so this can be justified because the user can actually see the differences. But when the user is in a poor network condition, so the return of this rendering effort start to decrease. So because it is not delivered to the user as it is. So this means that the server-side GPU resource usage is not always translated into the user perceived quality gain. So, and along with the qualitative one, so this quantitative result also supported that. So the bar shows the frame quality metric, so which is scored by the BMF. And then, so as you see, so as the rendering quality goes up, the gain is bigger when the user is in a good network condition. So this implies that the high quality rendering, so on the server side, not considering the user's network condition, can be resource inefficient. So it is important to optimize a resource allocation based on the network area and user perceived frame quality. And that's the opportunity Stimpack is observation Stimpack leverages. So and let's talk about the high level approach of Stimpack. So Stimpack assumes the situation where the GPU is shared by the multiple users. So as you see here, so when a single GPU is shared by the multiple game instances, so they submit the rendering command to the rendering queue. And then as the GPU works in the time multiplexed manner, so it iterates these queues to process the command, and the frame is rendered for each game instances. So when you think there are multiple concurrent users, so this causes the processing time for each frame get increased. So this technically drops the user's FPS. So this is observed with one of the result outcomes, so a result figure in our paper. So as we see, when there is only first user, so that user is served around the 90 FPS. But when there is a second user comes, so the rendering load becomes double, and then the user's FPS dropped by half. So as more user comes to the server, so it reaches to the point where it cannot serving at the playable FPS to the users. So Stimpack's approach is to optimize the load on the server side, so by adjusting the rendering quality. But when doing that, so Stimpack optimizes the rendering quality by balancing the user side frame quality and server side cost. So to do that, so Stimpack quantifies the resource efficiency with compression-aware and user-side frame quality prediction. So as you see here, so for the users with the relatively worse network conditions, so Stimpack just allocate the lower rendering quality. So technically, consuming the less resources for those users. And these reclaimed resources are used for the other users who actually can see the quality improvements. The optimization process of Stimpack has 3 pillars. And first one is the playability. So it is important in gaming use case to maintain the playable FPS. Then the second one is the visual quality. So while maintaining the playable FPS, it is also important to preserve visual quality. And the last part is around the system utility to maximize the system-wide resource efficiency. So through the prioritization when there are multiple users. So this one is the optimization objective, the process objective in the Stimpack, but I'll not go with that much detail. But so Stimpack works to maximize the aggregated efficiency score across all the users, which is defined by both the server-side rendering cost and the user-side quality gain. So this one shows the Stimpack's architecture. And it has the 2 main components. The first one is a plugin, which is integrated into each game instances, monitoring the FPS and actually controlling the rendering quality of that instance. And the other part is the Stimpack runtime, which is an engine running the optimization process, and so coordinating the rendering quality adjustment across the multiple users. So and how the Stimpack operates can be go with this simplified operational workflow. The first phase is the monitoring phase, where the captured FPS and compression parameter of each users are reported to the runtime in the regular basis. And then the runtime start to make the decision to allocate the proper level of the rendering quality across all the users. In this case, at that time, the runtime runs the optimization process. And technically, the previous SVC, the optimization function works over there. And the last part is when the decision is made, it is sent back to the user game instances, and then actually the rendering quality is changed. So it keeps running on that way. The evaluation of Stimpack is done on our testbed with 2 sample games powered by Unreal Engine. So the first game is with the moderate load, with the cartoonic style graphics. And the second one is more the intense load case, with the realistic and complex graphics. And in our evaluation scenario, we assume there are up to 6 users and 2 different arrival patterns. The first one is with a gradual arrival, which means that each user comes in a sequential manner with a time buffer. And this shows how incrementally how the Stimpack operate in that. And then the rest of the users come as simultaneously, which is the bursty arrival. And this also shows how the Stimpack adapts in that situation. And Stimpack is evaluated with both the static and dynamic network conditions. The performance evaluation, the first performance evaluation of Stimpack is for the scalability and FPS stability. The experimental goal is to measure the maximum capacity with same resource footprint. It is done by comparing the Stimpack against a naive baseline, which is setting all the game instances rendering quality at the highest level, which is inspired by the current existing services policy. While they're not considering the GPU sharing situation, but this serves as a proxy to evaluate how the current policies scales under the GPU sharing situation. The key finding of this performance evaluation is the Stimpack effectively prevents the FPS collapses. Even when the server is heavily loaded. When the baseline, for the baseline case, when there are all the 6 users comes here, as we see on the left side figure, the user's FPS drop to below than the playable FPS, which is set as 30 frames per second. But for the Stimpack's case, it starts to adapt the user's rendering quality, and then to maintain the user's playability. The first game is relatively with the moderate load, the capacity gain is not that much dramatic. Because even with the naive baseline, 5 users can be served with that. But with Stimpack, all 6 users can be served with the playable FPS. But the effectiveness of Stimpack gets more highlighted when the the game instances get more resource intense. So when there are only 3 users with the nice baseline, so for the second game, so which is with the intense graphics load, so the up to 3 users can be served with the playable FPS, and when the all user comes, so its FPS is really, really low, so it's really hard to see as a motion portrayal. So, but compared to that, for the Stimpack, so it starts to adapt the rendering quality, so and maintain the FPS. So in this case, the effectiveness is more highlighted. So the previous part is talking about the FPS stability and scalability. So because the experience in cloud gaming is determined by not only for the FPS, but also the visual quality affect that. So we conduct a more holistic the user study to evaluate the gaming experience evaluation. So in our user study, so each user is presented with the game state of serving game state, so which is the one from Stimpack, and from the others is the baselines. And this one is technically the blind A/B testing, and we measure the winning rate of Stimpack. So there were 3 baselines in our user study. One is the highest only case we already touched, where we're setting all the users' rendering quality at the highest level. So this one is the one extreme case compromising FPS for visual quality. And the other extreme is the lowest only case, setting the users' rendering quality at the lowest level. So this one is compromising the visual quality for FPS. And the third baseline is the DJ, which is one of the previous work. So it has a similarity to the Stimpack in that, so it adjusts the rendering quality to adapt the server's load, but it has a fundamental difference. So as it does not consider how the rendering effort is translated onto user-side quality. So in our user study, so Stimpack outperformed in most cases and confirming its effectiveness in balancing gaming experiences in terms of both FPS and visual quality. But there is one also noticeable thing, so because there is a subjective preference in gaming experiences, as we highlighted here. So some users preferred the smoothness, even with the very low visual quality, to moderate both visual and smoothness. So this also implies that there can be further opportunities incorporating the subjective preference to the system behavior for the better performance. We have the dedicated section in our paper, so if you are interested in, so please refer to that. And the last part of the evaluation is for the real-world adaptability of Stimpack. So we tested Stimpack with the dynamic network condition users, and we used the real-world 4G and LTE bandwidth traces. So, and out of these bandwidth traces, we generate the compression, the state traces, so and applied this for testing the Stimpack's operation. So the key observation is the Stimpack is quite effectively work even in these dynamic network condition cases. So the highlight thing is the Stimpack shows the dynamic prioritization. So as we see with the user 1 and 2 as highlighted on the figure here. So around the 200-second mark, so the user 1's network quality goes up, and then the user 2's network condition get worse. And this one is actually reflected on the rendering quality trace as highlighted on the right side. So Stimpack allocate the lower rendering quality for the users whose the network condition goes worse. And then this reclaimed the resources is allocated to the user 1 who actually appreciate the quality gain on the user side. And there is another flip on the later part of this trace, and this one is also reflected on that. So in summary, in Stimpack, it shows the high resource efficiency with the holistic system level optimization for cloud gaming. And to do that, it actively used the application level metric, which can capture the end-to-end aspect. So by doing that, it successfully bridged the gap between the server-side rendering cost and user-side quality. And it improved the per GPU scalability up to 2x users capacity while maintaining high QoE. One of the insights out of this work is that perception-aware efficiency matters. So Stimpack recognizes the rendering more does not always mean the user sees more. So this one is captured by as mentioned, the application level metric. And then by using that for the system level optimization, it achieved the high resource efficiency. So as we see, in this case, in network system, the server-side effort can be ineffective due to the downstream bottlenecks. So in our use case, the cloud gaming, it was the content delivery with compression. But this one can be applicable even for the other use cases. Yep, this is the end of the presentation. And if you have any question, I love to address them. And this one is the project repo QR code. Thank you.